So now that we've covered all the types of equations in two space, okay, for the vector world, we're going to now extend that into three space. All right. So what I'd like you to do to start with is you could either open up, okay, this day three handout here, or at the very bottom of this page. All right. If we go through the whole lesson and take a look at the very bottom, you'll see that we've got the equation right here, or the handout right here. What I want you to do is pause the video, right, and go through this on your own. Think about what needs to happen with each of these three tasks, okay? Task one, task two, and task three. And then once you've covered it, I'd say, you could probably take a look at this within about 10 to 20 minutes, all right? And then you can press play again and continue on, and we'll summarize what we need to summarize. So if we take a look at, all right, hopefully what you've done before, let's just review, all right, some of the things here, and I'll try to explain them as best we can, all right. So if we're just going to be taking a look at the vector equation, the parametric equation, and the symmetric equations, we notice that there's not much difference other than the addition of this third component, okay, that we have. So in 3D for the vector equation, instead of just xy, we have xyz, all right. For the point, if that's on the graph that we're using the a1, a2, it's a1, a2, a3. Right? And the direction vector has the third component, the m3 to it, all right? Because of that, there are now three parametric equations, okay, in 3D, all right? Three parametric, the x, the y, and the z. Notice that all the t is the same, the parametric, okay, or the parameter is the same. So when we convert to the symmetric equation, it works out to be, have this third ratio to it, right? Z minus A3 divided by M3. Okay, so those are the three. That's how they extended. That should be fairly straightforward. All right. Now, when we're looking at trying to take a line and intersect it with one of the major planes, the XY or the YZ or the XZ, all right, then what we need to know is that the third component is going to be equal to 0, okay, for this, for the equation themselves. So if we look at the parametric equation, for example, all right, if we want to intersect, let's say we're intersecting the x, y plane, all right, and you know that you've got z coming up here. Well, in this case, z is going to be 0 everywhere that's on the plane, right? So you're going to have some x, some y, but you know you're going to have 0 for sure, okay? So that means that the parametric equation needs to be equal to 0. This z is going to be 0, all right? And so if you know that z is going to be 0, then you can solve for t, the parameter, and then you know what to substitute back in to find your x and your y. All right, your x and your y here, you just sub that back into the t. Okay, and then you have it. So that's your strategy. All right, if you were to do it with, the y z plane, well, then you know that x is equal to 0 there. All right, the xz plane, if you want that, you know that y is equal to 0. Okay, this is identical to finding the x-intercept or the y-intercept when we did this way back in grade 9 or in grade 10. Okay, remember we said for all x-intercepts, y is equal to 0. For all y-intercepts, okay, x is equal to 0. All right. Well, instead of just intersecting the axes, we're intercepting a plane, right? So basically, if you wanted, you could say for all xy intercepts, right? Intercept of the plane, right? For the plane, the intercept, how you write it, the intersection point between the xy plane, we know that z is equal to 0. And you can do the same thing for the other two planes. Okay, so you know that. All right. The other thing just to take note of when task 3, all right, is when we are looking at um, having a line that's parallel to a plane, we notice that obviously with the direction vector now has to be 0, okay? Because again, if we take a look at the thing I have here, if a line is right on the plane there, notice that the z is 0, right? So a direction vector will have that z component being 0 as well. Okay, well, this causes a bit of a problem for the symmetric equation because you can't divide by 0. All right, so we adjust the equation a little bit. We don't have an equal sign from the one that's not going to or doesn't work well with us. We have a symmetric equation or a somewhat symmetric equation for the first two, and then we just have a comma and say, well, here's what z is equal to. All right, we know it's going to be equal to the A3. All right, how do we know that? Well, the direction vector is 0, right? If you take a look at the symmetric equation, you've got A3 plus t times 0, which is just A3. All right, that's the idea itself. So now, let's take a look at, here's what we're going to do. We are going to take a look at, all right, two lines. How do two lines relate with each other in 3 space? All right. Now, with these definitions, okay, I will have to the right, notice there's nothing there right now. I will have a link right here. There will be a link here. By the time you see this, there's going to be a link here. And it will give you a nice little demonstration of two lines in 3 space. If you can't visually think of it on your own, you can take a look at that link. Okay? But you see, we've got basically 4 things that could happen now in 2 space, or in 3 space rather. All right? We could have two lines that are parallel to each other. We can have two lines that are the same, they're coincident, they're, it's boring, right? We could have two lines that intersect, but now we have this fourth case, which is skew lines, and these two lines, they don't intersect and they're not parallel, all right? And I've said in here, if I was in class, I could do this with 2 meter sticks while I use 2 pens in the demonstration, okay? So again, take a look at that little video. All right, you can pause this before we move on if you need to understand what the skew lines are. Okay, but you are going to be, from here on, you're going to be looking at two lines. You could be given two lines, and they're either going to be parallel or the same line, or they're going to intersect or they're skew. They work in pairs that way. All right, because if you take a look at it, if we look at the conditions for what parallel lines need to be in 3 space, right, we know that the direction vectors must be scalar multiples of each other. Okay, now in this case I use an L1, L2, L3 for the first scalar. All right, but basically what you're doing is one direction vector has to be a scalar multiple of the other direction vector. Okay, and if they're parallel, if we take a look at just two simple parallel lines here, there's the point A that we know on this line here, we'll call it A1. Notice it is not on line 2, okay? We could have some A2 that we know that's on L2. If these are parallel, they're not on. A2 is not on L1, okay? If it were, they'd be the same line, right? If I were to have this, they're the same direction vector, and the two lines or the 2 points are on the same line, there you go, two lines, and they basically amount to be the same. We're going to have an example where we show that. Okay, it might be a little clearer when we go through the example. Let's take a look at intersecting lines. Okay, in 3 space, for them to be intersecting, here are the two things that we need to know. First of all, the direction vectors, okay, for those two lines can't be scalar multiples of each other, all right? We can't have this, so we say, no, this isn't true. And that's something we can just look at, all right, between the two if we're given the two lines. The other thing it's going to be tougher to prove here is that if they're intersecting, there is a point in common with them. There's one point. We don't know what that point is. It doesn't have to be the A1 point on L1 or the A2 point on L2. It's just any point, okay? If we don't have a point in common, then we have skew lines. Again, we'll take a look at an example with that, all right? Let's see. So let's just go through it. I'm going to go off to the side and we'll just make up some, well, we'll do the, we could do the parallel lines here. Let's do an example. One, let's take a look at two lines. Let's say L1 is going to be, we don't want an equal sign there. L1 is going to be x minus 1 over 2 equaling y plus 3 over negative 6. And we'll say z minus 5 over, I don't know, let's just go with, stay with 8, okay? L2 could be x plus 3 over 1, y minus 7 over negative 3, and z plus 1 over 4, okay? So here's what we do right off the bat, okay? We take a look at the direction vectors. We have M1, we know is 2, negative 6, 8, and M2 is 1, negative 3, 4. You can eyeball this, you can see this already, and you can see that M1 is 2 times M2, right? So there's a scalar multiple. Since they're scalar multiples, you can say, all right, L1 is either going to be parallel to L2 or L1 equals L2, all right? So that means that all their points have to be in common, all right? Well, we already know, that A1, which is 1, negative 3, 5, is on L1. We need to see if it's on L2, okay? So what we do is we're going to sub A1 into L2, and we're going to see if these symmetric equations hold true. So what we have is 1 plus 3 over 1 equaling negative 3 minus 7 over negative 3 equaling 5 plus 1 over 4. So we have 4 equaling 10 over 3 equaling 6 over 4, which is 3 over 2, and we know that none of those are true, okay? This means that we have L1 is parallel to L2, okay? If the symmetric equations were all equal, then we know that they would be the same line, okay? So that's how we have there. So that's the way of proving either parallel or coincident lines. Let's take a look at showing if they are intersecting or skew lines. So let's just say we've got an L1 being equal, or sorry, L1 is x minus 1 over 2, y plus 5 over 3, and z minus 2 over, let's say, negative 4. Okay, L2, we have x plus 3 over 3 y minus 1 over negative 2 and z plus 1 over whatever, 5. Okay, so here's what we have here. So we notice right off the bat, m1 is not a scalar multiple of m2. You can see that. Okay. How do you see that? Well, you know m1 is 2, 3, negative 4. You know m2 is 3, negative 2, 5. Okay, so there's no scalar multiple there. This implies that L1 intersects with L2, or L1 and L2 are skew. Okay. What we do is we assume that L1 intersects L2. Okay. We assume it and see if we're true or if we're not true. We can either determine the point or we can't determine the point. If we can't determine the point, then they're skew lines. We'll come up with a contradiction, right, if we can't prove it. So here's what we do. We know that the x's are the same at the point of intersection. The y's are the same at the point of intersection. The z's are the same at the point of intersections. So we use the parametric equations. Okay, so using the parametric equations, from the L1 side, we have 1 plus 2t is equal to negative 5 plus 3s. Oh, sorry, I skipped over. That's not what I want. That's from L1. The t side is the L1. For L2, we're going to get negative 3 plus 3s. Okay? The y's, from the y's, we've got negative 5 plus 3t equaling 2 minus, I did it again, equaling 1 minus 2s. And finally, we have 2 minus 4t equals negative 1 plus 5s. Okay? So here are our three equations. All right? We're going to solve for two of them and then see if our solution fits for the third. If it does, then we have lines that intersect. If it doesn't, then we have skew lines. Okay? So let's solve for, let's say we're solving for just s and t, or sorry, for 1 and 2. Okay? So I'll say from equation 1 and 2, I'm just going to rearrange this a little bit. I'm going to have 2t minus 3s equals negative 4, 3t plus 2s equals 6. All right. Let's just say we've got, I'm just going to rearrange 1 and 2 here. Let's say we go with 3 times equation 1, 2 times equation 2. So we have 6t minus 9s equals negative 12. We have 6t plus 4s equals 12. I need to subtract these. And so I end up with negative 13s equals negative 24. S equals 24 over 13. Then I can sub my S into, we'll say, the equation 1. So 2t minus 3 times 24 over 13 equals negative 4. 2t, let's see, we get minus 72 over 13 equals negative 4. 2t equals, what's 26 and 26? 52 minus 52 over 13 plus 72 over 13. 2t equals, that looks like 20 over 13, which means t is equal to 10 over 13. Okay, so we have our solution for 1 and 2. We take our s and our t and we substitute them into equation 2. So we're going to sub s and t into, equation 3 and see what we have. Okay, so 2 minus 4 times 10 over 13 equals negative 1 plus 5 times 24 over 13. If this is true, we have intersecting lines. Okay, so 2 minus 40 over 13 needs to equal negative 1 plus, I guess that's 120 over 13. Okay, well, this is, I can see is not true, right? 2 is 26 minus 40 over 13. This is a negative number, so that's negative 14 over 13. All right, this is negative 13 plus 120 over 13. This is a positive number, so we have 107 over 13. Not true. Therefore, L1 and L2 are skew. Okay? And that's the idea. If they were to be intersecting, right, then this final check here would work out that the left side equals the right side. We would know what our S and our T's were so that we could just substitute them into either side of our parametric equations and come up with what our actual components or coordinates of the point were. All right, and you'll probably have some questions like that. Okay, but that's the process. All right. The last thing that we're going to take a look at, all right, is a neat little special case, okay, where we're given direction vectors or direction angles, and we have a point that the line passes through, okay, and then we'll be able to get what the equation is based on this information, okay? So if you take a look at it, and I'll just talk it through in this case. Let's say, for example, the direction angles are these special angles that we have, right? Are 60, 45, and 60 degrees, okay? So the L1 has direction angles like this, okay? Find the symmetric equations for L1, right? Well, from the special angles, if you're taking a look at what the ratios are, cos alpha, remember, is cos 60, okay? Cos beta is the cos of 45, it's next. And then finally, the gamma here is the 60 as well, okay? So you end up with the 1/2 cos of 45, 1 over root 2. You rationalize the denominator, you get root 2 over 2. And then the cos gamma is 1 over 2 as well. What's special to note on this one is that if we notice the cos angles, the cosine, the direction cosines, all right, are these, where we have the components on top with the magnitude of the direction vector on the bottom. Okay, so when we rationalize the bottom in the second one here, we can see that we're getting the magnitude of 2. If we look at x, y, and z being the 1, root 2, 1, like we have here, we check the magnitude is correct. That means this is the direction vector. Okay, since this is the direction vector, we know we're given that it passes through the point negative 2, 1, and 3, then we have our symmetric equation that we need. Okay, it's a neat little case there that works out nice and compactly. All right. Anyway, take a look at these. All right, have your hand at showing lines are either parallel, coincident, or collinear, skew, or they intersect. intersect. Okay, good luck.